Hey students, proceeding to the other question, you are given a rectangular prism with edges made by three vectors u, v, and w as you see. The question is to find the area of its total surfaces. Students, as you know, a prism has 6 faces where a pair of three faces are basically having congruent area. So what we need to do is we first try to calculate, okay, three rectangular regions area, and then we just multiply that by 2. So the procedure goes like this. So the first thing that we need to do is, you see, we have to find the cross product of either u cross v or u cross w or v cross w as we wish. Anyway, the total surface area is going to be twice of the norm of u cross w plus the norm of u cross v plus the norm of v cross what? W. This is what we need to do, because the norm of the arbitrary two vectors of the given vectors make the area of the rectangular region, or the area of the face of what? The prism. That is what we need to do. So the total surface area is going to be 2 into norm of u cross w plus norm of u cross v plus norm of v cross w. So we are now forced to know or to determine these three. So let me show you how this can be done. First, we have to calculate v cross w. We have been given that v is a vector having component 2, minus 3, and minus 1. And vector w is a vector with component 1, 1, minus 3, as it has been given. Here it is, 1, 1, minus 3. So I, j, k components are going to be written. So u components are labeled here in the first row, and the w components are written in the last row, as you see. Now, what we need to do is we have to use the technique to find cross product between two vectors. So delete the first row and the first column. You are left with this in trace. So what we need to do is minus 3 multiplied with minus 3, 9 comes minus 1 times 1 is minus 1, minus makes plus, so you are left with 9 plus 1i, and then this minus comes directly because of this minus 1, and then delete the first row and the second column, then you are left with 2 times minus 3, minus 6, minus, you need to multiply negative 1 with 1, minus 1, so minus 6 minus minus 1 makes minus 6 plus 1, and coming to the last one, the k component, this is obtained directly by deleting the first row and the third column. During this case, you are left with these 4 entries. So what you need to do is you need to multiply the diagonals. 2 times 1 is going to be 2, minus, you need to multiply these diagonal entries, minus non-diagonal entries, minus 3 times 1 makes minus 3, so 2 minus minus 3 makes 5, so you are left with this. So when you take the sum of this, you are left with 10i plus 5j and 5k. So we need to find now v cross w, because this v cross w is required here, as you see. So the norm is the sum of the square of what? The components and the radical. So this is going to be the square root of 10 squared plus 5 squared plus 5 squared, which actually is 150, and that is nothing but it is 5 radical 6. Now coming to the second one, now we determined, you see this one, so we are now left with 2 norms. So let's proceed. Similarly, students apply similar procedure. Norm of u, the norm of u cross w can be obtained by using this approach. First, we need to label, you see, the components of u, 1 minus 2, 1, as you see. Components of w directly taken, 1, 1 minus 3. So you need to now find the cross product of the two, as I tried to explain earlier. And as you do that, you are coming across with this kind of expression: 6 minus 1i minus minus 3 minus 1j plus 1 plus 2k. So this makes 5i and plus 4j and 3k. So as you are looking for the norm of this, you are having the square root of 25 plus 16 plus 9. And this makes what, students? This makes 5 radical 2. So what is obtained now? The norm of u cross w is obtained. So now we determined the norm of the first one and the last one. So we are left with now the norm of the middle one. So now let's calculate the norm of u cross v. So as I did in the first two cases, u cross v is obtained directly by doing this, and applying the same procedure, we can come across with a vector with this output, students, 5i plus 3j plus k. So we need to look for the norm again. This is going to be 25 plus 9 plus 1, and this comes to be radical 35. So students, now we are having three outputs. One here, 5 radical 6, 5 radical 2, radical 35. Each represent the area of the faces. So we are having two congruent faces. So we need to multiply this by 2 in order to determine two of the faces of the prism, to the area of the face of the prism. You do the same here, you do the same here. So as you are doing this, you are going to take 2 times of this sum, these three sum. So you do have this one. The total surface area is going to be 2 times this one. The reason why we multiply by 2 is because we are having 6 faces. So 3 faces are already obtained. Since we are having identical faces, we need to multiply by 2. That is the reason why we are multiplying what? By 2. This is all about question number 5. What comes next is question number 6. And here you are asked to find the volume of the prism which was given in question number 5 above. So the H's are already determined. So what we need to do is, in order to determine the volume, we need to carry out the absolute value of the triple product of U, V, and W. Here you are free to use another approach too, like V dot U cross W or W dot U cross V, as you wish. As long as you are taking absolute value, in whatever way you may calculate, the result is the same. So we have to use absolute value. Don't forget that the volume of any sort of rectangular prism, not only that, volume should be given, okay, in terms of a positive value. So what is going to come now is this one. As we did before, V cross W is already done, students. The V components are, as you see, W components are as you see here. So the cross product of the two is already actually obtained. Here I repeat that. So 10i plus 5j plus 5k, please you can return back. And we knew the components of U. So the components of U are here, 1 minus 2, 1. So already V cross W is obtained. So you can take 10i plus 5j plus 5k. So you can take the components as you see. So the next task is a matter of finding the absolute value of the dot product of the two. So this is going to be 1 times 10, 10, then this is minus 10, and 1 times 5 is 5. So as you are calculating this, you are coming with number 5. So this number 5 shows that the volume of the prism, you see, made by edges of those 3 vectors is number 5. So the amount of matter that can be contained within the prism is 5 unit cube. And proceeding to the next one, we are having now another question, and that is this one, students, and it is about determining what, students, the certain. So here what we need to do is, you see, you are given three vertices of a triangle with A minus 1, 2, minus 1, B, 2, minus 1, 1, and C, 1, minus 2, 3. So you are asked now to determine the area of this triangle. From a certain fixed reference, consider origin, 3 points were taken as A, B, and C. So the question is to find the area of the triangular region made by these 3 vertices. So what we need to do is, students, we need to recall the concept of Cartesian products or cross products between vectors and its norms when we come to the area of a triangle. So we need to recall that. So what comes next is the solution. The solution goes like this. So what we need to do is the following one. So first we have to determine these 3 vectors, these 2 vectors, vector AB and vector AC. So vector AB is nothing but it is obtained by deducting, you see, components of vector point A from B, and that is obtained as you see like this. Vector AB is this one. So what you need to do is you have to subtract, you see, like you have to do like this, 2 minus 1, which actually is 3, and you proceed, negative 1 minus 2, 1 minus 1. So you do like this. This represents vector AB. So you need to, students? You need to deduct the terminal, the initial point from the terminal one. So you are left with this vector. Vector AB is going to be like this. Do the same for vector AC. For vector AC, you do the same. what you need to do is you have to deduct this 1 minus minus 1 to be positive 2, and here minus 2 makes minus 4, 3 minus minus 1 makes 4. So these two vectors are now given or obtained. What we need to do is we have to determine, we have to determine the cross product of these two vectors AB and vectors AC, because the cross product of vector AB and the vector AC can determine, students, the vector normal to these two vectors, vector AB and vector AC, and this norm represents the area of, the rectangular region. But as we are taking half of the area of the rectangular region, we are going to obtain the area of the triangle. So the area of the triangle is going to be half of the norm of the vector AB crossed with vector AC. So we need to now look for, the cross product of these two vectors, vector AB and vector AC. Have A here, students. So components of vector AB are 3 minus 3, 2. The components of vector AC are 2 minus 4, 4. So as we are looking for the cross product of these 2, you are having I minus jk, so label components of AB as 3 minus 3, 2, components of AC 2 minus 4, 4. Now perform cross product of these two. So as I tried to explain, for the first I component, delete the first column in the first row. You are left with this entry, so this is negative 3 times 4, negative 12, and this is 2 times minus 4, minus 8, minus 12, minus 8 makes minus 12 plus 8, as I wrote here. That minus comes, and again here what you need to do is for the j component, delete what the second column in the first row. You are left with 12 minus 4, which actually is 8, but you need to have minus in front, as I wrote here. And for the k component, delete the first row and the third column. You are left with minus 12 plus 6, right? So you do have now minus 6i minus 8j minus 6k as an output. So now we need to determine the norm of the obtained cross product. Look, as you are looking for the norm, what you need to do is try to take the sum of the square of these components. It's minus 6 squared, minus 8 squared, and minus 6 squared. In doing so, you can have 36, 64, 36. So when you add all this inside this radical, you're going to obtain the area of the rectangle. But you are now looking for the area of the triangle. The area of the triangle is half of the area of the rectangle. So what we need to do is take half of this, the obtained answer. So when you take half of the obtained answer, you are going to get the students? The area of the triangle. So the area of the triangle is going to be radical 39. Thus the area of the region is radical 39. Okay, students, let's proceed. Now comes another question, or another problem, and let's do that together. Question number 8 says, if the sum of two unit vectors is a unit vector, you are asked to find the magnitude of their difference. So here we are given two unit vectors, and we have been told that the sum of the two is a unit vector again. So we need to look for the magnitude of the difference of these two vectors. So please follow me how I'm going to do. So you have been told that the norm of u is 1 and the norm of v is 1. I just have taken the two vectors to be, u and v. So I have norm of u to be 1 and norm of v to be 1. And you have been told that the sum is again 1. So let's see how I'm going to obtain the norm of u minus v, or the magnitude of u minus v. But before I come to that, we knew that the norm of u plus v is 1, and we know that the norm of u plus v is the square root of u plus v dotted with u plus v, students. Remember, students, the norm of any vector u is the square root of the dot product of the vector together with itself, okay? So the norm of any vector u is the square root of u dot u. Similarly, the norm of u plus v will be the square root of u plus v dotted with u plus v. But as you are doing u plus v dotted with u plus v, you are having u squared plus v squared plus 2 u dot v. So basically, students, when I say u squared here, I mean norm of u the whole squared plus norm of v the whole squared. Please have norm here. So you have been told that norm of u is 1 because u is a unit vector, so you do have 1 here, and the norm of v is again 1, so 1 plus 1 makes 2. So you are having now 2 here plus 2 times u dot v, right? 2 times u dot v. So clearly, when you square both sides, you are having 2 plus 2 u dot v being 1, and as you are taking these two to the right, you are having now u dot v being negative 1 over 2. So u dot v is negative 1 over 2. Please have that as it is. Now when we come to the norm of u minus v, as I said earlier, the norm of u minus v, student, is the square root of u minus v dot with u minus v. So when you perform u minus v dot with u minus v, you are left with norm of u squared plus norm of v squared minus 2 times u dot v. So the same u and v are taken. So we knew that the norm of u and the norm of v are 1. So what we need to do is, you see, students, the square root of 1 plus 1 makes 2. So 2 minus 2 u dot v is going to come. But this is going to be the same as the radical of 2 is taken as it is. But as you know, u dot v is already known. It's negative 1 over 2. So 2 minus 2 times negative 1 over 2 makes 2 plus 1. And this finally makes radical 3. So if two vectors are unit vectors, and if their sum is also a unit vector, what happens to the difference magnitude? The magnitude of the difference is radical, what? 3. I hope simple. Now comes question number 9. Suppose you are given 3 vectors u, v, and w, and assume that the angle between these 3 is 60 degrees. Now, what this is just to say is that the angle between u and v is 60, u and w is 60, v and w is also 60. So, you are also given that norm of u is 4, norm of v is 2, and norm of w is 6. So, you are asking now to find the norm of the sum of what? These 3 vectors. So, this can be done by using this approach, students. The norm of u plus v plus w squared is u plus v plus w dot with u plus v plus w. So this is how it can be obtained. As I said earlier, the norm of u squared is u dot u. So when you carry out, you see the dot product of this, you are coming with this one. This basically is u dot u is norm of u squared, u dot v. Because of v dot u, you are having 2 u dot v. Do the same. But whenever you come across with, you see, dot product of identical, you see, vectors, don't forget to take the square of the norm. So you are having now this expression. Once you have this, what you need to do is, you see, this is the same as this one. You can take these middle terms like this, you see, you can write them as you see. Now, norm of u is already given 4, so square makes 16, and norm of v is already given 2, its square will be 4, and this is 6, its square will be 36, plus, you know that u dot v is norm of u times norm of v times cosine of the angle between the two. But you have been told that cosine of the angle between the two is cosine of 60, because the angle here is 60, and we knew that cos 60 is 1 over 2. You do the same for each of these 3, because you have been told that the angle between these vectors is 60 degrees. So what comes next is this. Look, students, I just wrote the first 3 as they are, but 2 is written, 2 is taken out, but u dot v is norm of u times norm of v cosine of the angle between the two, 60. You do the same for these 2. You are having now everything written in terms of a given information. So try to substitute the given information here. 16, because u is given 4, square is 16, v is 2, square is 4, and norm of w is 6, its square is 36. Then 2 is taken out. The product of these two, norm of u times norm of v, makes 4 times 2, 8, and cosine 60 is 1 over 2. You take 4. Do the same for the last 2. You are going to have 12 and 6. So as you are summing all this, you are going to get 100. Mind you, student, that this is the square of the question we are looking for. So we are having now 100. Since we are asked to find the norm of the sum of these 3, we need to take its square roots. So its square root is going to be what? 10. So whatever 3 vectors are given for us, if the magnitudes are labeled as you see, as 4, 2, and 6, and if the angle between any 2 of these 3 makes 60 degrees, then the norm of their sum is going to be 10. What comes next is question number 10. In question number 10, again here, you are given 3 vectors, u, v, and w. So the question is to find a unit vector, a in the direction of the given one, b in the opposite direction of this. So what we need to do is the following. First, students, we have to determine what u cross v plus u cross w is. So the solution goes like this, and we know that u cross v plus u cross w is the same as this one. U can be taken out, student. Then we do have this property. Instead of performing, you see two cross products here. What we need to do is first we take the sum of v and w, and then do one cross product. So this basically this one. First, let's determine v plus w. So v plus w is simply 2 plus minus 1, which actually is 1. 1 plus 2 is 3, and minus 1 minus 2 is minus 3. Now we need to take u, and here you see u cross v plus u cross w is u cross v plus w. So we knew what v plus w is, it's already done here. Then take u. U is going to be 1 minus 1, 1, as you see. Then as you are performing this cross product, students, as I tried to explain before, you are going to have this kind of output. Please, I have done this kind of operations before, so you need to go back and refer. So this is going to be 3 minus 3i minus of minus 3 minus 1j plus 3 plus 1k. So when you take this sum, you are left with 4j plus 4k. So this is, you see, the vector that is equivalent to u cross v plus u cross w. Now you are asked to find the unit vector in the direction of this. So if you are asked to find the unit vector in the direction of this, now let you ask yourself that this is what? Is this a unit vector? Basically, this is not a unit vector because its magnitude is not 1. So to change a non-zero unit vector, a non-zero and non-unit vector to a unit vector, what we need to do is we have to divide the vector by its magnitude. So we have to look for the magnitude of 4j plus 4k. Basically, look, the magnitude of 4j plus 4k is already taken. This is basically done in order to change, you see, a given non-unit vector to a unit vector, okay, except zero vector. So this is how it is done. So we divide this by its magnitude. So the magnitude of 4j plus 4k, as you know, is square root of 16 plus 16, which is radical 32, and that is 4 over 2. So we can take 4 as a common out and cancel by 4. We are left with 1 over radical 2 j plus k. So this one is student's unit vector, right? This is a unit vector because you can look for its magnitude, it's 1. So you are asked to find in the direction of u cross v and u cross w. Here we got. In the second case, you are asked to find in the opposite direction of this one. So what we need to do is the opposite vector to a given vector is the negative of what? The given vector. So you simply multiply the obtained vector by negative. And this is how it is obtained. So if we multiply the obtained vector by negative 1, we will get the opposite vector. So the opposite vector is going to be a matter of having minus, and it will be negative 1 over radical 2 j plus k. So these two unit vectors can be obtained in this case. Okay, proceeding to the next one, you are asked to find the cosine of the directional angles of the vector u, I minus 2j plus 4k. So what we need to do is we have to determine now the directional angles, okay? And basically we're not going to determine the directional angles. We are asked to find the cosine of the directional angles. So cosine of these angles are expected to be obtained. So first we have to determine the norm, right? The magnitude of the given vector. And so the magnitude of the given vector is the square root of what, students? 1 squared and minus 2 squared plus 4 squared. Because the components here are 1, minus 2, and 4. So 1 squared plus minus 2 squared plus 4 squared. So this makes 16 plus 4 plus 1. So it's going to be radical 21. So let's assume that alpha, beta, and gamma be the angles between the x-axis and the y-axis and the z-axis from the vector u. So from the cosine of directional angles, we know that cosine of alpha is going to be the I component here. That is to say the x component, which actually is 1, the coefficient is 1. 1 divided by the norm, which actually is radical 21. And cosine of beta will be the j component, which actually is minus 2, divided by the norm, radical 21. And cosine of gamma is the z component, which actually is 4 divided by radical 21. Since we are asked to determine cosine of the directional angles, so this by itself is enough. How can you assure whether the obtained answer is right or not? we know that these cosine directional angles direct the given vector, so the sum of the square of these outputs must make 1. So if you take the sum of all these three outputs, it makes 1. So in such a way you can assure. Basically, had you been asked to find the angles, what you need to do is you have to take cos inverse of these values. For example, in order to determine alpha, you have to consider cos inverse of 1 over radical 21. And if you want to determine beta, what we need to do is you have to look for cos inverse of minus 2 over radical 21. So here, since we are having a negative angle, it is well known that beta is an obtuse one. It is an angle between 90 and 180. But in the case of alpha, it is a acute angle because it's a positive measure. And when you come to gamma again, we have an acute angle, which actually is cos inverse of 4 over radical 21. So these three angles can be determined using calculator. Just bring a calculator and try to press the corresponding buttons in order to obtain the output. So you can know these three angles using a calculator. This is how you can find cosine of directional angles. Students, you have to underline here that finding the directional angles is quite different from finding the cosine of the directional angles. When you are asked to find the cosine of the directional angles, as I did earlier, you need to put your answer as I wrote here. You see, as I wrote here. But these are finding the directional angles. So this is all about question number 11. What comes now is question number 12. Here, you see, you are asked to find the distance between the point and the line. So this talks about finding distance between a point and the line. So what we need to do is like this. Students, in order to find distance between a point and a line, we need to use this formula. If you remember, students, we derived this in our classroom. Here, P naught represents an arbitrary point lying on the line. And P represents the point given, right? Whose distance is being looked for. And V represents the directing vector that directs the line. So using this, we can determine the distance. So here, your P naught can be taken to be minus 2, 2, and 0. The reason I took here minus 2 to 0 is because, you see, if you evaluate minus 2 here, it's going to be 0. So now again, think of the case where this can be 0, because we have obtained this to be 0, or we have determined this to be 0. But you are free to take another output. For example, if I take x to be minus 1 plus 2 comes 1. So I have to consider the case where, you see, this ratio can be 1. In such a case, you can determine y. So the same is true here. You see, z can be 1 in the case of this. So you are free to take any point that lie on the line. Any point, in order to obtain any point on the line, try to look for x, y, z values that can satisfy the symmetric equation of the line. So basically now, if I just consider 0, the value that can make this 0 is minus 2. The value that can make 0 is 2, and here the value that can make this 0 is 0. So I'm free to take minus 2 to 0 as an arbitrary point lying on the line. So no problem on taking a point lying on the line. You are free also to take another one. It doesn't have impact on the final output. So how about the directing vector? As you know, student, the directing vector in the case of symmetric equation can easily be determined from the denominator. So this is written as x minus minus 2. So the denominator is 1, so you can take 1. Here we are having y minus 2 over 3, so the denominator is 3, so you can take it as it is. Though we are having 0 here, this understood that this is z minus 0 divided by 1, so 1 can be taken. So the directing vector is this one. That is to say, your line is parallel to this vector. So everything is now available. P naught is available, minus 2 to 0, here we have. And P is also, you see, given. You see, this one is a given information, so we are having P here. And V is also obtained, so the next task is a matter of finding, you see, the cross product in the norm. So what comes now is P naught P. P naught P, the vector P naught P must be calculated, and it's a matter of deducting students? P naught from P. So our P is here 3 minus student? Minus 2. It will be 5, and here 0 minus 2, which is minus 2, and 1 minus 0, it is 1. So P naught P is 5 minus 2, 1. This is required because it has to be used here in my formula. Now comes V. What is V? Directly take this one, 1, 3, 1. So carry out P naught P cross with V. So as you are performing this cross product, students, you are coming with this vector minus 5i minus 4j plus 17k. I tried to explain how this can be done before. Please try to refer to the previous slides. So this p naught p cross v is going to be this vector. Since I'm looking for, this is the magnitude as it has been written, I need to consider the norm or the magnitude, and this is going to be the square root of the sum of the square of the components. Minus 5 squared 25, minus 4 squared 16, and 17 squared 289. So when you take this sum, students, you are going to have radical 330. So have this as your numerator value. Now you need to determine the norm of v. And the norm of v can be obtained simply taking the sum of the square of the components of v under radical. And we knew that v is having components 1, 3, 1. So if you take the sum of this square, you do have 1 plus 9 plus 1, as it has been written here, and this makes radical 11. Now, students, you have determined norm of v, which is required as a denominator here. You also have determined p naught b cross v norm, which is required as a numerator here. So the next task is a matter of dividing this by this. So the distance now is going to be radical 330 divided by 11. And this comes to be radical 30, students. So the distance between the point and the line is going to be radical 30. So students, whenever you are asked such kind of question, please apply this procedure. What comes next is question number 13. Question number 13 talks about equation of a line. In fact, you are asked to determine the two different forms of a line, symmetric and parametric. So you are now asked to determine the equation of the line, provided that the line is supposed to pass through the point minus 2, 5, 3 and perpendicular to the plane 2x minus 3y plus 4z equals minus 7. Now, in order to do this, there is one thing that you need to remember, students. The vector that is going to be normal to the plane is basically the vector that's going to direct the line, because the line, so long as the line is parallel to the plane, you see the vector needs to be parallel to the line. Okay, so you have to consider this concept. But as you studied in our classroom, the normal vector of a given plane can easily be known from the coefficients of x, y, z. So here the coefficients of x, y, z are 2, minus 3, 4. So these components are actually components of what? The normal vector to the plane, which indirectly are components of the directing vector to the line. So using parametric equation of the line, as you know, this is a parametric equation of the line as we derived in the classroom. So this is x equals x naught plus at, y equals y naught plus bt, and z equals z naught plus ct, where a, b, c representing the components of the directing vector, x naught, y naught, z naught is, this is the components of an arbitrary point on the line. So, as I said earlier, you can now take a, b, c to be these components of the vector, 2, minus 3, 4, and x naught, y naught, z naught, you are free to take minus 2, 5, 3. So substituting this in place of this equation, one can get this one. So this is going to be what? The parametric equation of the line. We call this parametric because the parameter t is used. But if you want to solve for t, students, you are going to come across with this expression. Look, just move minus 2 to the left. It's going to be x plus 2. And then divide by 2 to find t. You are left with x plus 2 over 2. Do the same for this. Y minus 5 divided by minus 3 can come if you solve for t. And finally, for z is equal to 3 plus 4t again, you can solve for t. What you need to do is move 3 to the left, and it will be z minus 3, and then divide the entire one by 4. You are left with z minus 3 divided by 4. So the symmetric equation is going to be as it is written. Okay, students, what comes next is another question, and let's talk about again solving question number 14. So you are given what, students? You are given 1 point where the line is going to pass through, and the point is 1 minus 2, 1, and you are supposed to now look for the equation of a line which is parallel to the given line and passing through the point 1 minus 2, 1. So let you follow me how I'm going to do. The solution runs like this. If two lines are parallel to each other, students, then their directing vectors are parallel too. So one is a scalar multiple of the other, students. So if one is scalar multiple of the other, we can directly take the directing vector of the other one as a directing vector for, you see, the line we are looking for. Simple. So the directing vector for the given line, x equals minus 1 plus 2t, y equals 3t, and z equals minus 2 minus t is basically what? 2, 3, minus 1. Vector 2, 3, minus 1. It is directly obtained from the coefficient of t. 2, 3, and minus 1. Now students, what follows is the directing vector 2, 3, minus 1 can also be used to direct the intended line. Basically, I can also use a certain scalar multiple of this one, but later it will be simplified. So we can directly take this directing vector 2, 3 with components 2, 3, minus 1 for, you see, the line we are looking for. So using the parametric equation of the line, as I said earlier, we can determine what? The equation of the line parallel to the given line. We know that x equals x naught plus at plus y equals y naught plus bt, z equals z naught plus ct is the general parametric equation where a, b, c are components of directing vector, x naught, y naught, z naught are components of the point lying on the line. So as it has been given, you see, ABC is a vector with components 2, 3, minus 1, and the point x naught, y naught, z naught is already given. It's specified here, as you see, 1, minus 2, 1. So the next task is a matter of now plugging these values in their corresponding place above. Then the parametric equation is going to be x equals 1 plus 2t. What I did here is I just put in place of x naught I just used 1, and in place of t I used 2, so 1 plus 2a, 1 plus 2t, sorry, can come. Do the same for y. In place of y naught you can take minus 2, and here b is now 3, so minus 2 plus 3t, and do the same for z. You are having this. So this is a parametric equation of what? The given line. Now if you are interested to determine the symmetric forms, just solve for t. So in order to solve for t, for the first one, for instance, you can move 1 to the left and have x minus 1 over 2. And for the second, you can have y plus 2 over 3, move minus 2 to the left, divided by 3. And then for, you see, the last one, you can move 1 to the left and divide the whole by minus 1, z minus 1 over minus 1. So the symmetric equation of the line can be as you see. Now what comes next is question number 15. You are given arbitrary 2 points where the line can pass through. The question is to determine the symmetric and the parametric equation of the line. So first we have to determine, students, the directing vector. The directing vector can easily be obtained simply deducting one point from the other, you see. So this can be obtained simply deducting one from the other, the components of 1 point from the other. For example, you can deduct minus 2 and minus 1. So you can have minus 2 minus minus 1, as I wrote here. And also 1 minus minus 2 and minus 1 minus 3. So students, for the first one you have minus 1, and for the second 3, and this one minus 4. So guys, you can take the directing vector components to be minus 1, 3, minus 4. The reason behind this is because if these 2 points lie on the line, you see the vector made by these 2 points is also lying on the line. So this vector can be parallel, or can be directing what? Can direct what? The given line. So we can consider like that. So our ABC now are minus 1, 3, and minus 4. So using the parametric equation of the line, one can determine what? The equation of the line. This is our governing what? Formula. So we are free to take A minus 1, B 3, and C minus 4 as I explained. C minus 4 as I explained here, and x naught, y naught, z naught, take an arbitrary point on the line. So you are free to take either this one or this as you wish. As you wish, whatever point you may use, you are going to obtain same equation, okay? So substituting these values in their corresponding places above, you can obtain the parametric equation as you see. X is minus 1 minus t, and y is minus 2 plus 3t, z is 3 minus 4t. So now students, if you want to solve for t, you come across with a symmetric equation. So its symmetric equation is going to be like this. Move minus 1 to the left, it's going to be x plus 1. As you see, if you minus 1, if you move minus 1 to the left, x plus 1, and divide by minus 1, t comes. So everything is solved for t here. Move again minus 2 to the left, y plus 2, and divide by 3. Move this 3 to the left again, z minus 3, and divide that by minus 4. So this is going to be the symmetric equation. So whatever points you may get as x, y, z, you see, if it can satisfy this, it is a point lying on the line, you see. If your if your numbers x, y, z can't satisfy this equation, the point you are considering is not lying on the line. So in such a way you can identify whether a given point is lying on the line or not. Now what comes next is question number 16. Here you are given a plane, students, 2x minus y plus z plus 2 equals 0. This is the equation of the plane. And you are given also a line, symmetric equation of a line, x minus 1 over 2 equals 1 minus y equals z plus 1 over what? Minus 2. So whenever a line and a plane are given to us, there are three possibilities. Either the line may lie on the plane, or the line may never intersect the plane, or there may be a situation where the line may intersect the plane at one point. In the case of this, the line will intersect the plane at one point, okay? The reason for this is because the directing vector of the line is not perpendicular to the normal vector of the plane. If it is perpendicular, it will be parallel, students. Anyway, or it may also lie on the line. It may also lie on the line. Okay, the line may lie on the plane. Okay. Now proceeding to the solution, students. Now it's known that the given equation is the symmetric equation of the line. You see. So we can adjust this to be t. X minus 1 over 2 equals 1 minus y equals z plus 1 over minus 2 equals t. So we can assign this to be t, as we did before. So when we solve this, we can obtain this one, look, students. So when we take each fraction, x minus 1 over 2 is equal to t. Now multiple by 2. So x minus 1 equals 2t, alright? 2t can come. Here, 1 minus y equals t can follow. And finally, z plus 1 equals minus 2t can come. Now, students, let's now write these three in terms of x, y, z. So in doing so, we can obtain this. Minus 1 can move to the right, and 1 plus 2t. Here move minus y to the right and bring t to the left, 1 minus t. And move this one to the right, minus 1 minus 2t. Now students, like you have been told that, you see, the line intersects the plane at one point. So what we need to do is, at the point of intersection, you see, the point must satisfy, you see, the point of intersection must satisfy not only the line, but also the plane, because it is a common point, it is an intersection point. So let's substitute the obtained x, y, z where in the equation of the plane. So substituting this in the equation of the plane to x minus y plus z plus 2, we can have this one, student, because x is 1 plus 2t, so we can directly put that there in x, and y is 1 minus t, so have minus in front, and then 1 minus t directly can be substituted, and in place of z you can take minus 1 minus 2t plus 2 equals 0 can follow. So students, as you see, the sum of this makes 3t plus 2, student, 3t plus 2. So when you solve for t, you are going to have minus 2 over 3. Once you obtain minus 2 over 3, what you need to do is you have to substitute to obtain the minus 2 over 3 there in x, y, and z expression, okay? So when you substitute that, you will obtain, students, when you substitute minus 2 over 3 there in x, in x here, you will obtain this to be you will obtain this to be a certain number. So have that one, and when you substitute again that, look, when just take minus 2 over 3 and substitute that here, and again take minus 2 over 3 and substitute here, and here might take minus 2 over 3 and substitute here. So you can now obtain the corresponding point, student, the corresponding point. So substituting that, one can obtain this. So the point of intersection is going to be negative 1 over 3, 5 over 3, 1 over 3. So do you confirm that the obtained answer is right or not, students? What you need to do is you have to substitute x minus 1 over 3, y 5 over 3, z 1 over 3 in both the line and the plane equation. It must satisfy. and you can verify that by your own. This is how it can be done. Okay, students, again, let's proceed. Coming next is question number 17. It says, find the equation of a plane containing the points A, B, C. These 3 points are given. So let's now find the equation of the plane. So simple. Since the points lie on the plane, the vectors AB and AC lie on the plane too. So the points here A, B, C lie on the plane. So the vectors made by AB and AC can also lie on the plane. But how can we find the vector AB? Vector AB is obtained simply deducting components of B from A, students. So I mean components of A from B. So what we need to do is 2 minus 1 is 1, as you see, and minus 1 minus 0, minus 1 minus 0 is minus 1. And 1 minus minus 1 comes to be 2, and come to this, AC is minus 1 minus 1, which actually is minus 2, 1 minus 0 is 1, and minus 2, minus minus 1 makes minus 1. So the located vectors, the position vectors are now known. So vector AB and the vector AC are now known. So what we need to do is we have to look for the normal vectors of the normal vector of these two vectors, because this is supposed to be normal not only to the vectors but also to the plane. Okay, so we can consider the output of this result as ABC because it's going to be normal to the plane. So let's calculate the cross product of AB and AC. So AB cross AC is going to be like this: 1 minus 1, 2 crossed with minus 2, 1 minus 1. So as usual, you have to label I minus JK here. So AB components are written 1 minus 1, 2, as you see, and AC components are written minus 2, 1 minus 1. So the I component can easily be obtained by deleting the first row and the first column, and this will be 1 minus 2 because this makes 1 and this makes 2, 1 minus 2 can come. And the J component is take the minus 1 in front and then delete the first row in second column, and you will get minus 1 and plus 4 because this makes minus 1 and this makes minus 4 plus 4J. And for the last one, delete the first row and the third column, you will obtain 1 times 1, 1 minus 2K. So finally you will obtain this to be minus I minus 3J minus K. So here, students, the coefficient of I, which actually minus 1, can be taken as A, and B can also be minus 3, and C can be minus 1. So this vector can be a normal vector to the plane because so long as the vectors lie on the plane, the cross product of the two vectors is not only normal to the vectors but also it's perpendicular to or normal to the plane. So what comes next is the following one. The equation of the plane can now be determined in the following sense: x minus x naught. Your x naught here is number 1. You are free to take this one. And y minus y naught. Your y naught is 0 here. And z minus z naught. Your z naught is minus 1 here. So this must be dotted with the normal one. This is a normal vector, and this must make 0. Because this is the vector lying on the plane and this is a normal vector, so the dot product must make 0. So when you calculate that, you are going to have minus of x minus 1 minus 3y minus of z plus 1 equals 0, and the final output comes like this. Now, dear students, I want to tell you something here. Before you confirm that this is the equation of the plane, make sure that this equation, the plane equation, can satisfy what those ABC coordinates, those points coordinates, please, because these points lie on the plane, so necessarily these three points coordinates must satisfy what the given plane equation. Good. Now what comes next is question number 8. In question number 8, students, you are asked to find the equation of a plane containing the point 1 minus 1, 2 and the vectors u and v. Basically the idea is the same, so we need to carry out the cross product of u and v, and that is supposed to be normal to not only the vectors u and v but also normal to the plane. And we do have here x naught 1, y naught minus 1 and z naught 2, so we can consider that point as ZC, a point lying on the plane. So using these two we can determine the equation of the plane. Let you follow me how I'm going to do that. So since the point 1, minus 1, 2 and the vectors u and v lie on the plane, we can calculate the cross product of u and v and consider that as a normal one. So the cross product of u and v is going to be, as I tried to explain earlier, the norm of the magnitude of I minus jk with 1, 1 minus 2, minus 2, 3, 1, actually the determinant of this one basically. And this is 1 plus 6i minus 1 minus 4j plus 3 plus 2k, and this makes 7i plus 3j plus 5k. So students, this is going to be normal to the plane. So what we can do is the following one. So what comes next is this 7i plus 3j plus 5k is already obtained. So now we can proceed. The equation of the plane is going to be x minus 1 comma y plus 1 z minus 2. Basically this is obtained as x minus x naught, your x naught is 1, and y minus y naught, your y naught is minus 1, so minus minus makes plus, so y plus 1, z minus z naught, so z naught is 2, dotted with the normal 1, 7, 3, 5. This must yield 0, so from this we can obtain this as student 7 into x minus 1 plus 3y plus 3 plus 5 into z minus 2 equals 0. And from this, the equation of the plane is obtained to be 7x plus 3y plus 5z minus 40 equals 0. So this is how you can obtain, okay, the equation of the plane. Now what comes next is question number 19, students. Here you are asked to find the equation of a plane parallel to the plane this and containing the point 1, minus 1, 2. So how are you going to find the equation of the plane parallel to the given plane? Basically what you need to do is, you see, the normal vector to the given plane must also be normal to the other or the intended plane. So if we are given, okay, that condition, so we can easily obtain the equation of the plane, because one point where the plane is going to pass through is also given. So the procedure goes like this. Since the two vectors are parallel, so the normal vector to one plane is going to be normal to the other, because the two are parallel, students. So basically the normal vector to the other plane is directly obtained just watching the coefficients of x, y, z. So the coefficients of x, y, z are 2, minus 3 and 1, right? They can easily be obtained from this one, x2, y minus 3, and the coefficient of z here is 1. So we can directly take that one as 2, minus 3, 1. Now students, you may consider this as a, b, c. And one point here lying on the plane is also given. So you are free to have here x naught 1 and y naught minus 1 and z naught to be 2. So the equation of the plane now can be determined by using this one. This is the equation of the standard equation, how the standard equation of the plane is going to be obtained. So x minus x naught, y minus y naught, z minus z naught, dotted with abc equals 0. So your abc are these values, 2, minus 3, 1, normal components, and x naught, y naught, z naughts are, you see, coordinates of the point, where you see the points lying on the plane, 1, minus 1, 2. So try to substitute these values here in their corresponding place. So here in place of a, have 2, in place of b take minus 3, and in place of c take 1, and here in place of x naught, y naught, and z naught, please take 1, minus 1, 2 respectively. So by substituting this, you see, you will come across with this kind of equation: x minus 1, y plus 1, z minus 2, dotted with 2, minus 3, 1, 0. Now what comes next is just to carry out dot product with the 2. So this x minus 1 will be multiplied by 2, plus y plus 1 is multiplied by minus 3, plus z minus 2 is multiplied by 1, and that has to be equated with 0. So you will get this expression. Then what you need to do is try to operate this and collect like terms together, and what you are going to obtain is this: 2x minus 2 minus 3y minus 3 plus z minus 2 equals 0. And then again, as I said, collect like terms together. You will obtain this to be 2x minus 3y plus z minus 7, in fact, yeah, because minus 2 minus 3 makes minus 5, and minus 2 minus 7, right, we are. So this is going to be the final output, okay, the equation of the plane. So how do you assure that the obtained answer is right or not? Try to watch the coefficients, students. If you observe the coefficients of the last output with the given one, you see they have the same coefficients. Look, the coefficients of x, y, z for the first plane is 2 minus 3, 1. Here we got also 2 minus 3, 1. This shows you that the two are parallel. Our d values are quite different. There it was minus 4, but now it's minus 7, so they are parallel in fact. And you need to check also whether you see the coordinates of the given points satisfying this or not. So when you substitute x1 there and y minus 1 and 2 in place of z, you'll obtain 7. And 7 minus 7 makes 0. So what we obtained is the right answer. Okay, students, now comes question number 20, and it is about distance between a point and a plane. So let's see how we can find this solution. Okay, so you are given a point and a plane is going to be determined from these 3 points, and we knew that these 3 points were given for you before. So we directly take the equation of the plane obtained before, and here you see, and then we try to find the distance between the given point and the plane. Okay, is how we are going to do. So the solution runs like this. The equation of the plane containing the point 1, 0, minus 1, 2, minus 1, 1, and minus 1, 1, minus 2 is determined already, students, because we have calculated this one in our previous video. Please try to refer that. And it is obtained as x plus 3y plus z is equal to 0. So what do you think is a normal vector here? The normal vector to this plane is a vector with components as a coefficients of x, y, z, and it's a vector with components 1, 3, and 1, right? Because as we take the components of x, the coefficients of x, it's 1, coefficient of y is 3, and coefficient of z is 1. So the normal vector to this plane is going to be a vector with components 1, 3, 1, right? So what is required here is to find the distance between this point 4, 3, minus 1, and this one, this plane. Okay, so what I need to do is first let's substitute 4 in place of x and 3 in place of y and minus 1 in place of z. Can you get 0? Students, you can obtain that because the sum of these the sum of this is going to be 4 plus 9, 13. 13 minus 1 is 12, so 12 is completely different from 0. This shows you that the point is not lying on the plane. If the point is lying on the plane, the distance is obviously 0. But now the point is obtained to be, you see, obtained to be or obtained as a point that never lies on the plane. So we can now calculate distance between the point and the plane. It is expected to be a non-zero value, right? So how is that obtained? This basically is obtained by using the obtained formula. Basically, we have derived this formula in our classroom, so I'm going to apply that one. So let me clarify the formula. D is standing for distance, so the distance between the points, you see, the point what? X, the point with the coordinate x naught, y naught, z naught, and a plane with equation ax plus by plus cz plus d can be obtained by using this formula. It is the absolute value of ax naught plus by naught plus cz naught plus d divided by the square root of the sum of the square of what, students? The coefficients of x, y, and z. So students, here in our case, we can consider a to be 1, b to be 3, and z to be what? C to be 1. Just take the coefficients of x, y, and z. And d is 0 because after z we don't have any number. That's implied that d is 0. And here x naught, y naught, and z naught are also given. Actually, they are components of the given point, 4, 3, and minus 1. So what we need to do is we directly substitute the given data here in place of their corresponding expressions or variables. So here a times x naught is required, a times x naught is 1 times 4, it is actually 4, b times y naught, we need to multiply these two. 3 times 3 makes 9, and c times z naught, 1 times minus 1, which actually is minus 1 as it is written. Then d says, so d is 0 because we don't have any number. You see to the right of this z, we don't have any constant. You see, how do we have that? We could have written that here. So d is 0, so I have that here. So square root of a square plus b square plus c square. So take the sum of the square of this, 1 plus 9 plus 1. So you are left with what? 13 minus 1, 12, and this is going to be 1 plus 9, 10, and 1, 11. So 12 square root of radical, 12 divided by the square root of 11 can come. So the distance between the given point and the plane is going to be 12 divided by square root of what? 11. This is how you can find distance between a point and a line, a plane. And coming to the next one, we have question number 21, and here you are given two lines, and you have been told that these two lines intersect each other. So you are asked now to determine the distance between the point of intersection of the first two lines and the other line, right? The other line. So the parametric equation, the vector equation of the two lines are given in terms of t and in terms of q. So we first need to find the the point of intersection between r of t and r of q lines. And once you obtain that point of intersection, you are asked to find the distance between that point of intersection and the line. So it's a matter of finding or understanding, or it's a matter of, recalling how you can find distance between a point and a line, okay? But here, what makes it different is we have to determine the point of intersection between these two lines, r of t and r of q, okay? So the process goes like this. So first, let us determine the point of intersection of the lines r of t and r of q. So for that, we have to have, to obtain the point of intersection, we have to consider, or we have to equate these two as t plus 2 to be the same as t2q, minus of 2t minus 1, the j component to match with the j component of the second one. So minus of 2t minus 1 being the same as minus of, students, minus of 2k plus 1j, and t plus 3 must match with q plus what, student? 4. Now, student, there is one thing that I would like to tell you as a correction. Please, students, take this correction here. Instead of taking the j component of rq as negative of 2k plus 1, please make it plus, okay? Positive of 2k plus 1, students. Make it positive of 2k plus 1. Because I have wrongly written here that the j component for rq is negative, so make it positive, please. So in that way, please correct it. Now we have to find values of t and q that can satisfy this, because this is the point of intersection of the two. Because this point of intersection must lie at these two lines. It is a common point, hence we need to look for, the values of t and q that can satisfy this. So from the first one, t is 2q minus 2. Alright? And from the last equation, as you see, from the last one we have t plus 3 equals q plus 4. So from this one, we can move 3 to the right, and t plus 3 equals q plus 4 can be t plus 3 equals q plus 4 can be what, students? 2q minus 2. So in place of t, I just have substituted 2q minus 2, because here in place of t, 2q minus 2 is used, plus 3 equals q plus 4. So from this q3 and t4 can be obtained, okay? q3 and t4 can be obtained. Once you obtain that, try to substitute there in their corresponding place. So when you substitute the obtained values there, you can have the following one, students. You can obtain the following one. So the point of intersection is going to be 2qi minus 2q plus 1j plus q plus 4, okay? So as you are substituting these values, you will obtain this to be 2 times q, which actually is 6, and here minus is taken. Actually it was plus, because this is directly obtained had it been plus, because this is directly obtained when it is plus. But now again it is reversed, Anyway, student, please try to understand, the procedure. Actually it was plus, but just understand that was plus, but consider it now as a -1 in order to keep every other step. So -7 and 7 can come, students. Right, yeah, proceed please. Now what comes next is, this is a point of intersection in order to determine that one. So the point of intersection, where is the point of intersection now? 6 minus 7, 7 is the point of intersection, students. So how are you going to obtain now this distance then? Once the point of intersection is determined, as we stated before, the distance between the point and the line can be obtained by using the formula D equals P naught P cross V norm divided by norm of V, where P naught is an arbitrary point on the line. So you are free to take arbitrary point on this line. So as we did before, try to think of the case where this all can be 0. And when x is 1, this comes 0. And when y is 0, it is 0. When z is 1, it's 0. So you are free to take 1, 0, and 1, students. 1 point lying on the line. And the corresponding directing vector v is going to be, you see, the one that is obtained as a denominator. So this is 2, directly taken. This basically is y minus 0 over 1, so you can take 1 here. But here you need to be careful. This is written as 1 minus z, so it's up to you to write z minus 1, right? So when you write this in terms of z minus 1, the negative comes down, and it will be -3, students. So you need to take -3 here. So the directing vector is given, v is known, and what else is known, students? This an arbitrary point p naught is known. So the corresponding intersection point you obtain here is considered to be P. So this P is 6 minus 7, 7. So we can determine now P naught P. So this P naught P is nothing, but it is deducting what, students? P naught from P. So what you need to do is like this: 6 minus -1, it will be 5. And again, -7 is deduct, -7 minus 0 is -7. And here 7 minus 1 is 6. So you are left with P naught P to be 5 minus 7, 6. So you need to carry out now cross product between these two, P naught P and V. So as you are doing that, your P naught P is this, and your V is 2, 1, minus 3. So as you are taking the cross product, you are going to have this vector, as you see, 15i plus 27j plus 19k. So we need to find the norm of this, because that one is required in the numerator there. So this is going to be 15 squared, 225, 27 squared, 729, and 19 squared, 361. So as you are taking the sum, you will obtain this to be 1315. So this is considered as your numerator value. Now you have to determine also the denominator one, that is the norm of v. And the norm of v is nothing, but it is a norm of what, students? It is a norm of this one, this vector. So 4 plus 1 plus 9 is going to be taken, and this makes radical 14. So the distance between the intersection of what? The distance between the point of intersection and the plane is going to be radical 1315 divided by 14, students. It is in this way that you can obtain. Okay, students, now comes question number 22. You have been asked that, show that the set of polynomials of degree 2 or less is a vector space over the field of real numbers under the usual addition and multiplication operations. So what we are expected to do here is we do have a set of polynomials with degree 2 or less. When we say with degree 2 or less, we mean no degree, 0 degree, 1 degree, and 2 degree, okay, functions, polynomial functions. So our set is going to have now collection of polynomial functions with degree 2, 1, and degree 0, and the case where we don't have any degree, like that of, you see, f of x is equal to 0, something like that, okay? So our field is the set of real number, okay? Our field is set of real number, and our operations are the usual additions and multiplication operations. So now we are going to verify that this set, the set of polynomials with degree 2 or less, is a vector space over the field of real numbers, okay? Basically, students, as you know, in order to say that a given vector, a given set of collection is a vector space over a certain field, there are 10 what? things that we need to assure. So if our vector is going to satisfy, or our collection of set is going to satisfy these 10 conditions, we call it a vector space, right? We can call it vector space. So first, let's see how V looks like. So your V is a set containing like this collection of elements P of X, where P of X is a polynomial function with degree 2, as you see, the degree is 2. So if A0, A1, and A2 are non-zero, you see, or especially if A2 is non-zero, it will be a quadratic expression. If A2 comes 0, yes, there is a possibility to have that. It will be linear, and if A1 and A2 comes 0, you are going to have a constant function with degree 0, except if A0 is different from 0. But in the case where A0 is 0, it will be what? A polynomial function with no degree. So having this into account, now you are asked to verify whether this is, you see, a vector space or not. So actually it's a vector space, so I'm going to show you that over the field F, over the field real number. So the first is a closure property. As you know, take arbitrary two functions from, or two elements from V. So when we take two elements from V, we are going to take two polynomials from this. So when we take the sum of these two, so whatever two polynomials you may take, you see, the degree is again less than or equal to 2. So the sum is again where students in V. So closure holds true. Closure property holds true. So when you come to the second, in the case of second, take an arbitrary element from V. So take a function f, which actually is a polynomial with degree less than or equal to 2. Take an arbitrary real number from the field. Now multiply this polynomial by a scalar number, you see, a real number. So what is going to come? Clearly, the coefficients are going to be multiplied, no change on the degree. So again, as long as f is taken from V, alpha V is going to be again where students in V. So closure can also happen here. And coming to the third, take arbitrary two elements from V. So take two functions f and g. So the third assures whether, you see, the elements inside V can have quadratic property or not. And obviously we know that f plus g is the same as g plus f. The sum of two functions as f plus g is the same as g plus f, as we know. So commutativity holds true. The third is a case where, you see, this associativity property holds true. So take arbitrary three functions f, g, and h, which actually are polynomials. So the f plus g plus h is the same as f plus g plus h. It's true because addition has associative property on functions. And proceeding to the fifth one, students, when you come to the fifth, for whatever, you see, function you may take within V, there exists, it says, an identity function 0. Again, in V says that the sum can be what? This, it is true, because f of x equals 0 is, or a function equals 0 is, you see, a function with no degree. Since you have been told that the degree is less than or equal to 2, it can be considered. So a zero function is part of what, student? This V. So for whatever function you may take, there is an additive identity, a zero function that makes what? This to be true, f plus 0, the same as f, which is 0 plus f, true. So this holds true, and when we come to the sixth one, it is talking about additive inverse. For whatever polynomial you may take, the additive inverse is negative f. It's a matter of multiplying each term by negative, right? And that is again where in V, because it doesn't have impact on the degree. So negative f is the additive inverse. So negative f is the left inverse in the case of this, and here it is the right inverse. So the inverse of f is minus f, and it is existing again in f. So this is also holding true. And coming to the fifth, take an arbitrary two real numbers A and B. Students, take arbitrary two real numbers A and B, and for whatever two real numbers you may take, and an arbitrary function f. A times B times f is the same as A times B times f. Yeah, it holds, because this is simply a scalar multiplication, so it holds true. So again, for arbitrary two functions f and g taken from V, and an arbitrary number alpha taken from the set of real number, you know that this property holds true. You can verify this by taking different examples. Basically, this is true. And coming to the ninth property, for arbitrary two elements taken from the field from the set of real number, take one element from what? From the V, that is, take one function, and a plus b times f is the same as af plus bf, true. Remember, combinations of functions is also hold true. And coming to the tens in the last property, for whatever a polynomial function you may take, multiplying, you see that polynomial by 1 is the polynomial itself. This is 100% true. So as can be shown, our collection or our set V is satisfying all these 10 properties under the field, under the operations of addition and multiplications over the field of real number. So we can conclude that this V is a vector space over, you see, a field of real number. But students here, if at least one of these 10 fails, we can say that V is not a vector space. So showing a vector space is somehow, you see, tedious. It might be long, because you see, you must assure these 10 conditions. But in order to show that a given collection is not a vector space, it is enough to show at least one of these 10, being, not satisfying. So it's so simple when we encounter question of, not showing a vector space for a given collection compared to showing a certain collection being a vector space. So this shows you that the given set is a vector space. I hope you have understood. What comes next is question number 23, and here you are given this collection, okay? So the question is to show that this is what, students, is not a vector space under the operation of addition and multiplication over the field of real number. So actually I just have written 10 conditions as you saw before, so it is enough to have only one condition. If one condition fails, automatically we can say that V is not a vector space. So let me show you how this can be verified. So as I wrote here, it's enough to show that at least one of the 10 conditions is failed. So in the case of this, let you take the closure property, whether it is closed or not. Take an arbitrary element from V, so 0, 0, 1 is taken, yes. If you substitute x0, y0, and z1, this is satisfied, so this is an element of V. And you can also 1, 0, 0. You can also take 1, 0, 0, because 1 plus 0 plus 0 is 1. Again, this is an element of V. So if you take the sum of the two, do you think that sum belongs to V? Let's check. So if you take the sum of the two, you are going to have 1, 0, 1, because 0 plus 1 is 1, and 0, 0, 0, and 1 plus 0 is 1. So as you see, this is not part of this V, because for an element to be part of this V, the sum must make 1. But if you take the sum here, it will be 2. So this is not an element of V, so clarity fails. Because of this, we can automatically say that V is not a vector space. Or one can also take another one. You may take, for instance, the origin 0, 0, 0. So additive identity must exist there, but this doesn't satisfy this one. Hence, the additive identity 0, 0 is not in V, because the sum can't make 1. So because of the absence of this, additive identity, we can also say that it is not a vector space. You can also take another one, but this having one of these two by itself is enough, okay, students? So this is how it can be verified. And coming to the next one, question number 24, you are again given a certain collection of ordered pairs, as you see. Now you are again asked here to show that this collection is not a vector space over the field of real numbers. So as I said, you are free to take one of these 10 possible conditions and show that it is failing. So the solution goes like this. Let's consider, look, an arbitrary number 1, 1 here, an arbitrary ordered pair 1, 1. We know that 1, 1 is an element of V, because x is 1, which actually is positive, and y is also 1, positive. So it is an element of V. So if you take -3 from the set of real number and multiple 1, 1, you are going to obtain -3, -3. And this -3, -3 is not in V, because for an ordered pair to be in V, both x and y must be greater than or equal to 0. But what we obtain here are both negatives, so This is not in V, so it's not closed, right? Scalar multiplication is not closed. Because of this, this is not a vector space, students. So in such a way we can verify, okay? We can verify whether a given collection is a vector space or not for the given operations under the given what? Field. Okay, students, let's continue. Now again, you are asked to show that the set of integer is not a vector space over the field of real number, okay? So the collection is now integer numbers. So let's see what's going to happen. So here it's enough to bring one case where at least one of the axioms, those 10 axioms, can fail. So let's consider the case of this one, scalar multiplication. So now take an arbitrary integer because our set is collection of integers, so we can take one arbitrary integer. Let's say a, b, an element from the set of integer, or a is an integer. Now take k to be an arbitrary real number. Now the question is, do you think that a times k is again an element of integer? That is a question we need to know. But this may not work always. Look, for instance, if you take a to be 5 and k to be radical 3, 5 times radical 3 can't be integer. Okay? Even you are free to take k to be rational numbers. For instance, if you take k to be 1 over 2, and if you take a5, 5 times 1 over 2 is 5 over 2. And how dare 5 over 2 is an integer. So, you see, I just have taken one simple approach. You can also take others, students. But if at least one fails, we can say that a given collection is not a vector space. So basically here, because of this one, you see, we can say that the set of integer is not a vector space over the field of real number. Here I just have taken one example. I took a is 3 and k radical 2. 3 is an integer, students, and radical 2 is a real number. So when you multiply these two, 3 radical 2 can come. And this is not an integer, basically. It is a real number, which is not what an integer one. So this shows you that the given set is not, set of integer is not, you see, a vector space over the given over the field what of real number, or under the usual addition and multiplication. Now comes another one, question number 26, students. Question number 26. So you are given here v as a function, students. So v is a collection of functions from real number to real number. It is denoted by function g. And w is another collection. It is, see, a collection of g from real number to real number, where g of minus x is the same as g of x for all x an element of real number. The question is w a subspace of v over real number? So what we need to do is, you see, students, here w is a collection of even function, because it is even functions behavior, you see, behave in this kind. So do you think that the collection of this even function can be a subspace of this v? That is the idea, okay, students? So how can we now do this one? So in order to do this, students, there are certain things that we need to assure. Basically, a subspace is what? A subspace is a subset of another vector space. And also, it has to be a vector space by itself, right? So, what we need to do is we are now going to check whether W is a vector space or not by using what? Those 10 conditions. Rather, there is an important theorem, so I'm going to apply that one. So, take an arbitrary 2 elements from what, students? V. You may consider here W. Okay, take an arbitrary 2 elements from students W. Basically, this is not V. Make it W, please, students. Then if f is an element of v, if f is an element of w, students, f of minus x must satisfy f of x. And if v is an element of w, students, if k is an element of w, sorry, k of minus x must satisfy k of x. Now let's talk about the sum. The sum of f and k makes what? F plus k of minus x. And this is the same as f plus k of minus x is the same as f of minus x plus k of minus x. This is a property of functions. But we know that f of minus x is the same as f of x, and k of minus x is the same as k of x, because both f and k are taken from w. Please correct this by w. Now, f of x plus k of x is nothing but it is f plus k of kx. So look, f plus k of minus x is the same as f plus k of x. This shows you that f plus k belongs to what? W. So causality holds true in the case of what? This. Now let's come to the scalar multiplication causality. Take an arbitrary real number alpha and multiply that by f. So this is the same as alpha times f of minus x because f is taken from w. So if f is taken from w, f of x is the same as f of minus x. So here alpha times f of minus x is going to come. So these two holds true. If this is so, f is an element of w. So the first condition is satisfied, the second condition is also satisfied. Now what comes next is the existence of identity function. If you take f of x 0, students, the identity function, the zero function, again, f of x equals 0 is the same as f of minus x equals 0 because this function is a constant function. For whatever you see value you may substitute it in place of x, f of x is 0, the output is constant. So what if we assign minus x? It is still 0. So if this is so, f of x is obtained to be f of minus x. So this shows you that f of x equals 0 is the same as f of x, f of negative x. So here again, you see f is an element of w. Because of the above assertion, we can automatically conclude that w is a subspace. W is a subspace of the vector space V. That's it. Now again, we are having question number 27. It says that show that the set of homogeneous solution of the system of equations, okay, the system of equations given by this is a subspace of the vector space RQ. So what we are going to do is first we need to identify the sets. So the set is a collection of what, students? The solutions, right? So we have to solve this one. So directly sum the equations given. If you take the sum of these, the sum of these two equations, what's going to happen is the following. Look, y minus y equals 0, so x plus x is 2x, and here 3z plus minus z is 2z equals 0, so 2 can be cancelled by 2, and z equals minus x can come. So if z is minus x, now look, we can substitute in one of these two. So substitute that in the second one, z is minus x, you substitute minus x here, this turns to be plus x, so what's going to come is x plus x, 2x minus y equals 0 can come. So solving for, you see, y comes 2x. Now students, I am able to write my solution in terms of x, y, z. And this x, y, z can be x is taken as it is, y is written in terms of 2x, and z is written in terms of minus x. So I can write my collection solutions here in terms of one variable alone. Look, w now can be written like this, x, 2x minus x. Look, w is a collection of all possible solutions for this. So all possible solutions now can be written in terms of this. So if you put x there as it is and put y 2x and z minus x, these two can be satisfied. So for whatever real numbers x you may take, you see you do have here a lot of points, and these points can satisfy this one. So now let's verify that this is, you see, a subspace for the given one or not. So as you see, let's take arbitrary 2 entries from this one because clarity must be assured. This is the first task. Take one element from this one. For example, if I take a variable n, it will be n to n minus n. It's an element of w. For an element to be part of w, you see, the first entry must be multiplied by 2 to be considered as the second one, and the third entry is the negative of the first one. Do the same, just change the variable x by m to m, and minus m is again in w. Now the question is, do you think that the sum can also be here in w? Let's check. So the sum of these two is going to be basically n plus m, and you can take 2 as a common out, then plus m can come, and minus m is the same as minus of n plus m. So yes, it is closed under the operation addition. For whatever two elements you may take, the sum is again, we are students, in w. If you consider here again scalar multiplication, take alpha to be any real number. So if you multiply that by an arbitrary one element here, you will come across with this expression. Look, the first element is taken as it is, but it has to be multiplied by 2 to be part of the second one, so it is multiplied by 2. And the negative of the first should be taken as a third component, so it's done as you see. So again, this is in w, so clarity holds true. So this is what I explained earlier. So look, n plus m to n plus 2 minus n minus m. So this is written in terms of what? The way how the elements of W are written, okay? So yes, true. Now let's assure the existence of identity, student. The zero vector 0, 0 can also be, you see, a member of W, because as you know, if you put 0, again 2 times 0 is 0, and minus 0 is 0, so 0, 0, 0 is 0, see, being an identity one. It's a matter of taking x0, students. So an identity vector 0, 0, 0 is also there, so it can satisfy all these conditions. In order to say that a given what, students, a given set is a subspace of another vector space, what you need to do is you have to assure the closure-ity of addition, the behavior of closure-ity property in terms of addition operation, and you need to also show that the scalar multiplication of what, you see, the given elements to exist in the given what, in the given sets, and the third is the existence of an identity one. If all these are satisfied, we can say that a given collection is a subspace of the given vector space. Therefore, we can say that W is a subspace of what? The V. Okay, students, now comes question number 28. It says, show that W given by this is not a subspace of R cubed over R. So now let's check whether this is not satisfying the subspace condition or not. So the solution goes like this. Here, it's enough to show that at least one of the subspace condition is going to fail, okay? So let's consider closure-ity property. Take an arbitrary element from W, 1A0. Yes, 1A0 is a vector with 1A0 is part of W, okay? For an element to be part of W, the first entry must be 1. And you are free to take any real number as the second entry, and 0 must be the third one. So 1A0 belongs to W, and take another one, 1B0 is also in W. Now what happens if we take the sum of the two? Look, if I take the sum of the two, 1 plus 1 comes what? 2. Now comes the deviation, you see, happening. For this to be part of W, necessarily the first component must be 1. But here it says what, student? 2. Because of this is not in W, okay? This is not in W. So the given W is not a vector space. A vector space. You see, I mean a subspace of the given vector space RQ. You can also take another approach. Even you can also have this as additional one. Take any real number A here and multiply that by what? An arbitrary element taken from this one, 1y0. If you multiply that, you will get ay0. For any number a different from 1, this is not in W, students, because if you take a to be a number different from 1, it doesn't belong to what? W. Because of this is not a vector space, I mean a subspace. And that is it. Moreover, the identity element 0, 0, 0 is not in W. You see, so I just brought three different situations where this is not filling out, but it is enough to bring one only. Anyway, this given W is not a subspace of R cubed. So what comes next is the other question number 29. Let you take A and B as you see. Now the question is, do you think that the union of these two can be a subspace of R2? Let's see. Take again here, students, let's consider again the case where you see one condition being failed, and that is, consider for instance this what? Ordered pair 1, 2. Clearly 1, 2 is an element of A, because when you put 1 there in place of x, 2 times 1 is 2, so 1, 2 is an element of A. Take again another element 2, 1, you see, because when x is 2, y can be 1, so 2, 1 can be an element of B. Students, please correct this one by making B, okay? This is B, whereas this one is A, this one is B. Now if you take the sum of the two, 1, 2 plus 2, 1, it will be 3, 3. And we know that 3, 3 is not an element of the union. Because for an element to be within the union, you see, either the first component must be twice of the second one, or the second must be twice of the first. But this is not the case. 3, 3 is not, you see, behaving this kind. Because of this union is not what, students? A subspace. So there is one thing that I would like to tell you as a tip here. Whenever you unite two subspace of a certain vector space, the union may not be a vector space. But this is not true in the case of intersection. The intersection of two subspaces of the same vector space is always a subspace to that vector space, students. So please understand that. And coming to the 30th question, we have this. Show that the following are bases for, you see, the vector space R cubed, and you are also asked to find the dimension of this vector space V. So the given, you see, set is this one, a set containing these entries 1, 1, 0, minus 1, 2, 1, 3, 1, 1. So in order to show that a given set of collection of entries is a basis for a given vector space, what we need to do is we have to show two conditions. One, you see, the given elements must be linearly independent. Two, the given elements must span or generate any elements within students? Within the given vector space, or every element within the given vector space must be generated by the the given elements in the set. That's why we call them bases. So let's now check the first condition, that is to say the linear independent case. So take arbitrary three coefficients a, b, c from the set of real number, because we are having three elements here, students. Because of this being three, we are going to take three coefficients a, b, c. Now let's take the linear combination of these three and equate with zero vector. So as you see, a times 1, 1, 0 plus b times minus 1, 2, 1 plus c times 3, 1, 1 equals 0 can follow. And from this, what comes is this one. If you simplify this, students, a times 1 is a, and here minus b and 3c. So a minus b plus 3c can come. This is a plus 2b plus c can come. And here, this is 0, and this is b and c. b plus c equals 0 can follow. So this has to be students? This has to be equated with the 0 vector. So if the only condition for this to happen is when three of them, A, B, and C, are 0, then we can call this collection linearly independent. But if there is a possibility where, you see, you can have at least one non-zero value A, B, C, this collection is linearly dependent, okay? That is the idea. Now let's equate, okay? Let's equate. Necessarily, a minus b plus 3c, the first entry must match with 0, the second entry must match with the second one, 0, and the third entry must match with the third one. So b plus c is 0. So from this, b is minus c. From the third equation, students, from the third one can obtain simply that b is minus c. And here, if b is minus c, students, look, if b is minus c again, come there. If b is minus c, come here, substitute that b minus c in place there. Then you are going to have 2b plus c equals 0. So look, 2b plus c comes 0, just adding these two downward, students. Look, student, if you directly add the first two, or subtract the first two, sorry, if you subtract the first two, a minus a is 0. So, yes, student? Look, let me just explain. If you subtract these two, a minus a is 0, and if you subtract upward, a minus a is 0, 2b minus b, 3b, and what's happening here is c minus 3c will be minus 2c. You see, you can have this one. 3b minus 2c equals 0. So from this, one can obtain that b equals c. Okay, b equals c can come. So if b equals c, student, and b is minus c, can equate c with minus c, and you can bring this minus c to the right. C plus c comes 2 times c equals 0. So c comes 0. If c comes 0, student, b also is coming to 0. So b is 0, c is 0. So you can substitute 0, 0 in one of these two. So you will obtain a being 0. So a comes 0. So everything here, or the coefficients a, b, c, look, a, b, c comes 0. It is when all these three coefficients are 0 that we can attain this 0. Otherwise, we are unable to obtain, you see, 0 condition or 0 vector. This shows you that these triple, you see, entries are linearly independent. Okay, so the first is assured. Now what comes next is the case where students, the case where the other is, you see, the case where the spanning condition is going to happen. Okay, the spanning condition is going to happen. So let me show you that. The spanning condition is going to be considered like this. Take an arbitrary element from R cubed. Now, can we construct, okay, can we obtain this element xyz by taking the linear combination of a, b, c using these three given components? Let's see that. Look, now we have to unite these three and take coefficients a, b, c in order to form xyz. xyz is an arbitrary entry taken from R cube. So do you think that these three are building blocks? Do you think that these three are bases in order to generate any arbitrary entry in R3? Let's check. So what we need to do is we have to determine a, b, c in terms of xyz, because xyz are components taken from R3. So we have to look for the case where we can solve a, b, c in terms of xyz. So this is going to be, when you add the left one, you will obtain a minus b plus 3c plus 2b plus c b plus c, and the right one is xyz. So adjust everything as we did before. So we are going to come to this situation. So let's now try to solve for ABC. So we are going to determine ABC in terms of xyz. So look, from this 3b minus 2c equals y minus x can be obtained. How is this obtained? Just subtract the first two upward. A minus a is 0, 2b minus minus b is 3b, c minus 3c is minus 2c, then y minus x can come, you see? And from the third, we have b is z minus c, right? So what comes next is, look, we are having 3b minus 2c is equal to y minus x, here we got. But we know what b is, it is z minus c, so we can substitute that b here. 3z minus c minus 2c equals y minus x. So from this, we can have 3z minus 5c, because minus 3c minus 2c makes minus 5c, y minus x. Mind you, our intention is to find these three values, a, b, c in terms of x, y, z. Now I'm running to solve for c, so c is going to be like this. Now look, y is known, x is known, z is known. You see, x, y, z are given. So your c is going to be negative 1 over 5 of this. Now let's try to come to b. You have been told that b is z minus c, directly taken from the third one. So z is taken as it is, now minus, what is c? C is already obtained here. The matter of taking this one and substituting and evaluating this one, you finally come across with this. So you repeat this, Now c is known, b is known. Can we determine a? Yes, you can substitute in one of the first two expressions or equations. So from the first equation, a is x plus b minus 3c. Just move minus b to the right, 3c to the left. You do have x plus b minus 3c. So x is taken as it is, but we knew what b is. You can copy this one and paste here. And minus 3c is taken, and we knew what c is already obtained there. So as we are operating this, we will finally come across with this kind of expression. So now students, a is obtained, b is obtained, c is obtained. So if you take a, b, c expressions and substitute here, look, a is obtained, b is obtained, c is obtained. So whatever x, y, z, you see, whatever element you may take from R cube, it's a matter of taking a, this one, b, the obtained one, c, you see, the obtained expression, together with these building blocks, these bases, you see, to form this x, y, z. So whatever x, y, z you may take, you see, these three can be building block in order to make this x, y, z. It's a matter of taking a, this expression, b, this expression, c, that expression. For example, if you take x1, y2, and z3, you see, a now can be obtained by using this one, x1, y2, z3. So you will get a certain output for a. Put here y2, x1, z3. Again, you will obtain a certain output for b. And for c2, you can substitute 2, 1, 3 there, and you will obtain a certain number. So let you take these three numbers, a, b, c, and put them here, a in place of a, b, and c. And if you operate that together with this, you will finally obtain 1, 2, 3. So a, b, c are actually coefficients, so we are able to determine any element of R3 in terms of what? In terms of these components. So for any x, y, z, an element of R cubed, as you see, we can write that x, y, z in terms of a, b, c, a times 1, 1, 0 plus b times minus 1 to 1 and c times 3 1 1, as you see like this. Okay, I just have substituted the obtained ABC values in place of ABC. Okay, nothing is done. Hence, from these two conditions, we can say that this is a base. In order to know the dimension, we have to know the number of elements within this collection. The number of elements here, as you see in the base, is 3. So the dimension of the given vector space is going to be 3, because the dimension of the vector space is the number of elements in the base. Mind you that the base can be of different kinds, but the number of dimension for a given vector space is fixed, is always the same.